In example 1, we've got some information about temperature of bacteria and the rate at which it's growing or replicating. And before we begin, it's worth looking at a graph of what this data looks like. So I've plotted the graph. On the horizontal axis we've got T, and on the vertical axis we've got G, the growth rate. And it is quite clear from this graph that it is an exponential model because the gradient of the graph is getting steeper as we move to the right. So this part where it says the data are coded using the change of variables x and y, what it basically means is they've sketched a graph of, rather than t on the horizontal axis and g on the vertical axis, they've sketched the graph of x against y, or y against x, where x is t, and on the vertical axis they've plotted log of g. And then this part where it says the regression line of y on x can be found to be that, basically means that when they plotted these points, they all lied on a line, or this is their line of best fit, something like that. Okay, so that's what this question is getting at. The regression line is a line of best fit. So let's have a look at part A. So this person thinks that because minus 0.2215 on the regression line means that the colony is shrinking when t equals 0, when the temperature equals 0. So we need to try and explain why this is wrong. Well, if we look at this relationship that they found, at the moment this is a relationship between x and y, but actually we know that y is log g. So let's replace y with log g in this relationship, equals minus 0.2215 plus 0.0792, and x is actually t. So this gives us a relationship between log g and t. So this might help us answer the question. Well, if the colony is shrinking, this means that the growth rate would be negative. Growth rate negative. So what we want to try and do to explain why she's wrong is actually show that the growth rate's positive and show that the colony is actually increasing in size. Well, the key part here is we're asked to find the growth rate when the temperature is 0, so when t equals 0. So let's substitute that in. When t equals 0, we get that log g equals minus 0.2215 because this term here disappears when t equals 0. Now remember that we're using log base 10, we're just not writing it each time. So in order to find g, we can do 10 to the power of both sides. So we can do 10 to the power of log base 10 of g equals 10 to the power of minus 0.2215. And the reason why we've done that is because 10 to the power of and log base 10 are inverse operations. So we get that g equals 10 to the power of minus 0.2215, and we get that that's 0.6. So when t equals 0, the growth rate, g, is greater than 0. So that means that the colony is growing. So we'll write that in a sentence. Growth rate is positive. So colony is growing. Okay. In part B, we're asked to find the missing values k and b in this model. So we're told that this is the actual model, and we need to find the constants. So let's take this equation that we get given. This is the equation that we know is true, And we know that y is log g, and that's minus 0.2215 plus 0.0792, and x is actually t. So that's one relationship that we definitely know is true between log g and t. Well, we need to basically convert this model into this form so that we can compare to find out what k and b are. So the way that we do that, and we do it the same every single time, is we take logs of both sides of the exponential model. So we get log g equals log of k multiplied by b to the t. And we'll use a log law to write that as log k plus log of b to the t. And then we'll use another log law to bring the power of t down, so we can write that as t log of b. So again, we've got two different ways of solving this problem. Method 1 would be to compare the two equations that we've got. So method 1, we know that that equation is true for the model, and we also know that that equation is true for the model. So the two equations must be the same as each other. So if we compare the two equations, we've got log g on the left-hand side, and we've got something multiplied by t. So that something is 0.0792 in this equation. And in this equation, we're timesing log b by t. So we know that log b must be equal to 0.0792 because these equations are the same. And remember, it's log base 10. So to find out what b is, we can do 10 to the power of both sides to get b equals 10 to the power of 0.792. So we can get a numerical value for b, if we work that out, which is 1.20 to 3 significant figures. And then we can also compare the constant term in these equations. The constant term in this equation from our regression line is minus 0.2215, and if we compare that to the constant term in this equation, it must be equal to log k. So remember, it's log base 10, so to find the value of k, we can do 10 to the power of minus 0.2215 to get the value of k. We can work that out. So k is 0.600 to 3 significant figures. If we were to use method 2, method 2 just uses the relationship that you find from the regression line. So we want to rearrange this regression line equation to get g the subject. So let's rewrite it out, and then we'll try and do that. And remember, we want it in the form g equals k b to the t. That's what we're aiming for. So let's get g on its own by doing 10 to the power of both sides. So we're going to do 10 to the power of log base 10 of g equals 10 to the power of minus 0.2215 plus 0.0792t. And then on the left hand side, 10 to the power of log base 10, they cancel each other out, so we just get g equals, and then we're going to use the rule, index rule, where if we've got 10 to the power of a plus b, we can split that up into 10 to the power of a times by 10 to the power of b. So here we're going to split this up into 10 to the power of minus 0.2215 times by 10 to the power of 0.0792t. So it's clear that this 10 to the power of minus 0.2215 is going to be k. So we'll leave that at the start. And then we want this second part to be in the form b to the power of t. Well, the way that we can do that is we can write that as 10 to the power of 0.0792 and then to the power of t. Because if we were to simplify this, we would times the two powers together and end up with what we originally had. So from this, it's clear that in our model, k is equal to 10 to the power of 0.2215, and this b part is 10 to the power of 0.0792. And then you could work out the same numerical values that we did in method 1. It's worth noting how they found this regression line, because in the exam you might not necessarily get given this equation and you might need to try and work it out. So what they've done to get that regression line is they've created a new table of data. They've left t as it is because we knew that we were plotting t on the x-axis, and they've replaced g with log g. So for example, to work out this numerical value there, they've done log of 1.04. And then they drew a line of best fit through the points. And it turns out that actually these points, I know it doesn't look like it from my drawing, but these points lie in a straight line. And then they got the equation of that straight line by finding out what's the gradient of that straight line and what was the intercept.